So far, we have seen how to multiply and divide unlike terms, in which the only difference is that the powers of the countees are different. The same 3 is here and here, but the power of 3 here is 2, and the power of 3 here is 1. What about unlike terms, in which the main difference is that the countees are entirely different? The powers might be the same thing, but the countees are just not the same. Let us look at such unlike terms that differ in every way. Now take a look at these new sets of numbers. 6 bracket 3 to the power 2 and 3 bracket 2 to the power 3. They are unlike terms, just like the former set. This time around, the countees are different and even the powers are different. The most important thing is that the countees are different. That's being counted by the coefficients is different. Whether they have the same power or different powers, we don't care here. What we care about is that at this point in time, the variables that follow are now going to be different. As you can see in the next line, that is a pair of numbers, 6x to the power 2. Let this 6 remain where it is, and let this 3 be x. So 2 to the power 2 now becomes x to the power 2. Then this 3 is still where it is. Let this 2 be equal to y, and so we have y to the power this 3. 3 is a constant. Therefore, let this in its pure constant form turn to this and this, which are in their algebraic forms. I want us to know whether the conclusion we reached before regarding the addition or subtraction of unlike terms is correct. Recall we said that addition and subtraction of unlike terms is not possible. They do not simplify out. Now that we are faced with different sets of unlike terms, are they still going to be not simplifiable? Let me carry out new sets of numerical experiments that will help us know whether that statement is valid at all times, whether the statement is correct anytime we are carrying out addition and subtraction of unlike terms of all kinds. Don't forget that this is a different set of unlike terms. Let me repeat the addition and subtraction of these two terms, 6 bracket 3 to the power 2 and 3 bracket 2 to the power 3. And find the first one. This is addition of these two unlike terms. 6 bracket 3 to the power 2 plus 3 bracket 2 to the power 3 by default is equal to 6 bracket 9. I hope you know where this 9 is coming from 3 to the power 2, that is this 9, and 6 is still where it used to be. Then what about this one? 3 bracket 8. 3 is still where it is, but 2 to the power 3 is 8. 2 to the power 3 is 8 because 2 to the power 3 means 2 times 2 times 2, and that will give us this 8 here. I hope how this became this is clear, and how this became this is also clear. 6 times 9 is 54. 3 times 8 is 24. 54 plus 24 is equal to 78. Therefore, the answer to this number operation is equal to 78. What if I replace this 3 by x and replace this 2 by y? Can I go beyond it to get any of these intermediate results? And can I even get 78 as the answer? Alright, permit me to replace 3 by x and this 2 by y. And let's see whether it is possible to cast the answer in any of these intermediate or final results. And here the corresponding addition comes. 6x to the power 2 plus 3y to the power 2. Is it possible to cast the answer to this number operation in this form? That is, 6 is still there, see it here. Is there anywhere 9 and 8, both of which on the bracket can combine to unify and form one thing? The answer is no. 6 is counting how many 9s and 3 is counting how many 8s. it is difficult to unite both of them. They are just independent numbers. One does not depend on the other. Because of that, it is practically impossible for this 9 and 8 to unite. If it is 6 nines and 3 nines, we cannot say that the total is equal to 9 nines, since the same 9 is being counted. If it is 6 eights and 3 eights that we are talking about, we cannot say 9 eights. But in this case, it is 6 nines plus 3 eights. Except we get the results separately, we cannot get this last answer. Because of that, x to the power 2 and y to the power 2 are completely not like terms. Based on that, this statement, 6x to the power 2 plus 3y to the power 2, can't be taken further. Except by coincidence, they have constants that have common factor. We can't simplify further, but if they do, we can do so by factorization. But that is not exactly what we mean when we say that the thing is supposed to simplify out. Based on that, we can't take 6x to the power 2 plus 3y to the power 3 further. Therefore, the result is irreducible. And that is it. 6x to the power 2 plus 3y to the power 3 is irreducible. Subtraction is a special type of addition. If I replace this sign of addition as used here with sign of subtraction, the same thing is going to be the last thing. That is the same conclusion is what I'm going to reach here. If it is 6x to the power 2 minus 3y to the power 3, except to factorize, which is by coincidence or by chance, we cannot reduce this to anything simpler. Because of that, we conclude again that addition and subtraction of unlike terms are not simplifiable. That is, they do not simplify out, irrespective of the manner in which the two unlike terms differ. So whether they differ by having the same symbol but different powers, or they differ by having different symbols in the same or different powers, addition and subtraction of unlike terms is not possible to produce a simple answer. Let us look at the multiplication of unlike terms possessing different symbols, the same power or different powers as the foregoing cases. Please watch out. And here comes the multiplication of the foregoing unlike terms. That is this times this. 6 bracket 3 to the power 2 times 3 bracket 2 to the power 3 is equal to 6 bracket 9 times 3 bracket 8. I hope you know how this came from here and how this one came from this expression. 6 bracket 9 is 54 and 3 bracket 8 is 24. So the whole thing is equal to 54 times 24, and the result is 1296. If we have a different way of getting this result of 1296, and it remains consistent afterwards, then it becomes a law of multiplying this sort of unlike terms. Let's try out. 6 bracket 3 to the power 2 times 3 bracket 2 to the power 3, when expanded, is equal to, this is 6 here, see it, 6 times 3 times 3, that is 3 times 3. Then times this 3 here, see it here, then times 2 times 2 times 2. It is by coincidence that what is here is also here, but this number is that which is here. The reason why I will not count this one as 1, 2, 3 is that it is possible for something else to be here. So I'm going to isolate this 6 and this 3, see them here. Because the confusion here is that in putting 3 to power to index form, somebody could be tempted to say that this 3 times 3 times 3 is 3 to the power 3, without knowing or taking note that something else, a different number, could have been here. It is just by coincidence that what we have here is 3, and 3 is also at this point, meaning this bracket. Because this 3 could be a different number, it should not be collected together with these two, which are in this bracket, see 6 and 3 in isolation. 6 times 3. We now have 3 times 3 is 2 to the power 2. We now have 2 times 2 times 2 to the power 3. Therefore, this number operation was simplified further will give us this. But that is not the last we can get. 6 times 3 is 18. Then times 3 to the power 2, see it here, times 2 to the power 3, see it here. As a result, we're saying that the result of this number operation is 18 bracket 3 to the power 2 bracket 2 to the power 3. We'll simplify further. 18 times 9 times 8 is equal to the same thing, 1296. The same number we got when we used the default method to get that multiplication done. This means that if we replace this 3 by x and this 2 by y, that how far we can go to get the correct answer is this. We cannot get this 1296 because by then we will not know what x is and what y is. Now watch as I replace this 3 by x and this 2 by y, and then carry out the similar multiplication. The brief process is here. 6x to the power 2 times 3y to the power 2 to the power 3 is equal to 18x to the power 2 y to the power 3. See it here. This 6 is here. This 3 is x. This power 2 is still where it is. Times is still there. 3 is here. This 2 is this y to the power 3. So this is algebraic alternative of this pure arithmetic expression. And then if this expression gave us this answer, knowing that any place we see 3, we replace it with x, and any place we see these 2 as the base, we replace with y, it thinks that this is equal to the same 18. See it here. This 3 is x, 10 to the power 2, and then 2 is y, 10 to the power 3. Therefore, this times this will give us this. What did you observe in this number operation that led to what we have here? First, this 18 was gotten by saying 6 times 3. The two constants which are present when multiplied will give us this 18. This 18 is just a case in point because different things could have been here, but because we have 6 and 3, the answer is 18. The next is that x and y did not just join, instead they were juxtaposed. That is placed side by side, the same way 2 to the power 2 and 2 to the power 3 were placed side by side. Therefore, with this multiplication of unlike terms that differ in both symbol and power is possible. What then will you say is the law for multiplying unlike terms that differ both in symbol and power? Let me use this space to write that conclusion. And here comes the conclusion. AB to the power x times CD to the power y. A is supposed to be a constant, just like this C, while B and D are supposed to be variables, and then x and y are their different powers. Of course, you see that this expression conforms to what we saw when we carried out this numerical experiment with multiplication. So how is it? Have 6 times 3, the same we have 8 times this C, see it here. Then we have this x to the power 2, then juxtaposed but with this y to the power 3. Likewise, b to the power x juxtaposed with this d to the power y, see it here. Therefore, what happened here is summarized here. The last is division of unlike terms that differ in both symbol and power. And here comes that division. 6 brackets 3 to the power 2 divided by 3 brackets 2 to the power 3 is equal to 6 bracket 9 divided by 3 bracket 8. And that corresponds to 54 divided by 24. The result is equal to 9/4 when evaluated. This is by default. And it works all the time when there is no variable replacing any of these numbers that feature in this number operation. Let us see if we can get the same 9/4 using an alternative method. Let's try. We have 6 bracket 3 to the power 2 divided by 3 bracket 2 to the power 3. Same thing as saying 6 times 3 times 3 times 1. This is 6, have it here. 3 to the power 2 means 3 times 3. This 1 is included just to equalize the number of times more numbers multiply up and down. This is 1, 2, 3, 4 times. The same 1, 2, 3, 4 times. Anyway, by association, we can isolate this 6/3. See it here, 6/3 10 times 3 to the power, because 3 times 3 times 1 is same thing as 3 to the power 2. Then 2 times 2 times 2 is same thing as 2 to the power 3. Therefore, this number operation has become base. The next thing is to divide this 6 by this 3, and we have this 2, while this 3 to the power 2 and 2 over 2 to the power 3 remains the way it is. This is how we come to 2 bracket 3 to the power 2 over 2 to the power 3. And when further evaluated and recast, it is something as saying 2 bracket 3 to the power 2 over 2 to the power 3. And the result is equal also to 9/4. Please confirm that if you evaluate this, what you get is 9/4. The same number or the answer we got when we used the default method to carry out this number operation. Let me now replace this 6 bracket 3 to the power 2 with 6x to the power 2 and replace this 3 bracket 2 to the power 3 with 3y to the power 3. And here the result comes. It says 6x to the power 2 divided by this 3y to the power 3 is equal to 2x to the power 2 over y to the power 3. Which of these intermediate results of this second line of operation does this represent? In fact, this is the same thing as this one, while this is this. Which of these results did I write in this form? Obviously, it is this one. Therefore, since this is equal to this one, this also is equal to what you have here. It therefore means that under some conditions, division of unlike terms can simplify out. And later I will tell you when that will not simplify out. Don't forget that at all times, multiplication of unlike terms simplifies out, whether the unlike terms differ in symbol or differ in power. Having observed this end result, let me write the law that appears to summarize the division of unlike terms in which the counties are different and the powers of the counties might be the same thing or different. Let me use this space for that summary. And here comes that summary, which is also a law. AB to the power x divided by ct to the power y is equal to a over c. See it here. Then bracket b to the power x over d to the power y. See it here also. Let us see whether this well captured the procedure and the result of this last line of action. Right? This is our a in this case is 6 and our c is this 3. How did these two come to be? It came by saying 6 divided by 3. That's the same thing as saying a over c. 6 over 3 is same thing as saying a over c. See it here. That's how these two came to be. I hope you're following. Then next, have this x to the power 2 over y to the power 3. And that corresponds to this b to the power x over this d to the power y. And that is exactly what we have at this point. This is the list of follows that guide us each time we want to consider addition, subtraction, multiplication, and division of unlike terms. Here you see that It's only multiplication and division that keep featuring throughout the four conclusions. What it means is that addition and subtraction don't simplify out in the case of unlike terms, no matter the type of difference that the like terms have, the unlike terms have. Before we take some examples that will help us see how to apply these laws, let me present a kind of general statement that explains these four lines, these four conclusions here, knowing that addition and subtraction are absent in that list. Please watch out for that general statement. And here comes that statement, which we could regard as the law of unlike terms. These are the laws of unlike terms in terms of laws of multiplication and division of unlike terms. But this can summarize all of this and can refer to it as the law of unlike terms. What is it? Addition and subtraction of unlike terms do not simplify out. Multiplication of unlike terms always simplifies out, while division of unlike terms simplifies out only where the constituent constants have a common factor and or where some symbols are alike. Please take your time to analyze this statement in the light of what we've been doing all along. With this alone, you can find out how to tackle unlike terms each time they appear in number operations. Most important is this first statement, that we don't get anything simple when we add or subtract unlike terms. So each time you add two numbers and they are unlike terms, please don't expect an answer. Each time you subtract and the numbers that are taking part in subtraction are unlike terms, please don't expect a simple answer. This first part of the statement is one of the most important points that I made in this body of statement. At this point, let us consider some examples of number operations that we can carry out with these four laws in mind. And here come the examples that will help us see how to apply rules of multiplying and dividing unlike terms. Already we have known that addition and subtraction of unlike terms are impossible. That is, they don't produce anything single or simple at the end of the process. Number one, we have 7y to the power 2 times 3y. Is it possible for these two to produce anything simple? That is, does the multiplication of these two numbers simplify out? Let's find out. First, are they like terms or unlike terms? They are unlike terms. What makes these two unlike terms? Just that the powers are different. That is all that makes this term and this term unlike terms. The same symbol, y, but this is power 2, this is power 1. Based on that, it falls in the category of this first one. This first law tells us that when multiplying two unlike terms in which the symbol is the same, but the symbols might differ in power, this is how to go about it. This is how to simplify the process. So let our A be this 7, our B is this y, our x is this 2. You can tell the rest. The power of this B, which is this y, is 1. So in the end, we have 7 times 3, just as we have A times this C. So A times C here corresponds to 7 times 3. And that gives us 21. Next is the variable. That common variable here is B. But B is the power x here and B is the power y. Likewise, the common variable here is y. Y here is the power 2 and y here is the power 1. So we have to write y. Then the power of the y we're going to have is going to be by adding the powers of the constituent powers of the common variable. Here we have power 2, here we have power 1. So our x plus y will give us this 2 plus 1, and that will give us 3. Therefore, 7y to the power 2 times 3y is equal to 21y to the power 3. So based on this law, this answer is correct. Example number 2, we have minus 2x to the power 2 times 5x times minus 3x to the power 3. The same law 1 is going to help us to get this. This example 2 highlights the fact that this law is not applicable only when we have two terms multiplying. That even if we have more than two terms multiplying and there are like terms, that the law is still applicable. Here we have three terms, this, and this multiplying. The same thing is going to happen. So let the constants multiply the same way A and C multiplied. The constants here are minus 2, 5, and minus 3. So minus 2 times 5 is minus 10. Minus 10 times minus 3 is 30. So the constants, when multiplied, will give us this 30. Then isolate that common symbol, which is the x in this case. See the x here, and add their powers. What would it be? Power 2, power 1, power 3. That will give us 2 plus 1, that is 3. 3 plus 3 will give us this 6 here. Therefore, when these numbers multiply, the result is equal to 30x to the power 6. In fact, without even remembering this law, it's possible for you to look at the pattern developing here and apply same in multiplication of any other set of unlike terms that have this resemblance. Example 3 is next. 12c to the power 5 divided by minus 4c to the power 2. Which of these follows is going to help us to simplify this number operation? Certainly, it is this. Why is it so? The constants are different, A and C. Likewise, we have this 12 and minus 4. In fact, the A and C can be the same. But because we have A and C, they could be the same or different. Being different is the most extreme thing that can happen. That is why we chose to use A and C. But if what is here is what is here, the law is still going to be valid. So next we have the same B here and here. Likewise, we have C here and C here. That means that this law is going to help us simplify this number operation. What is it going to be in place? When minus 4 divides this 12, the same way C divides this A here, what we get is minus 3. I now hope you know why this minus 3 is here. Next, C is common to both of them. I isolate it the way it was done here, and B is that common in the law. So this B is now this C, which we have here. What we do? Subtract the powers. Power of C here is 5, and power of C here is 2. So the power of this answer that corresponds to C will be 5 minus 2, and that will give us C to the power 3. Therefore, 12c to the power 5 divided by minus 4c to the power 2 is equal to minus 3c to the power 3. The next is number 4. We have ax to the power 3 times gx to the power minus 1. This example 4 highlights the importance of the fact that we must not always have constants as coefficients. In almost every case here, we have constants that serve as coefficients. Here, we have 1 in each case serving as coefficient. And when 1 serves as coefficient, it is as if we don't have a visible coefficient. This is why this number 4 is a special case. Therefore, we have ax to the power 3 times gx to the power minus 1. Which of these laws do you think is going to help us to simplify it? It is still this one. Why is it so? It is because the coefficients a and g might be different, but they have common symbol. This is x, this is x. Because of that, a times c corresponds to a times g. See it here. Then common b in this law corresponds to common x in this example. See it here. And then if we add the powers corresponding to x plus y, what we get is 3 plus minus 1. 3 plus minus 1 is same thing as 3 minus 1, and that will give us 2. Therefore, ax to the power 3 times gx to the power minus 1 is equal to 8gx to the power 2. Let us see example number 5, and that is 3e to the power 2 times 2f times 4g to the power 3. Which law is going to help us to see how to get the answer to this number operation? Is it still this one? No. Why? Because here we have b here, b here, suggesting that the variable, that is a symbol here and the symbol here are the same, except that they might differ in the powers. But if you watch this one, the symbol here is E, the symbol here is F, the symbol here is G. It therefore means that this is not what we're going to make use of in simplifying this number operation here. Instead, this is what we're going to make use of. This is used carrying out number operation in multiplication between two unlike terms that do not possess the same symbol and they possess different powers. See it here. So A, C, that is constant times constant. That means first multiply all the constants. There could be more than 2 taking part in that multiplication as we have here. If that happens, this law has not become invalid. This is in fact what this number 5 seeks to highlight, apart from having different symbols. Let's continue. So the first thing we get is the value of the product of the constants, which in this case are A and C. So in example, we have 3, 2, and 4. That means we say 3 times 2, that is 6 times 4, that will give us 24 first. Then next, treat the variables and their powers here. We'll have variable b to the power x, variable d to the power y. Likewise, we'll have variable e to the power 2, variable f to the power 1, variable g to the power 3. So what next? Just juxtapose them and their powers. That's why we have 24 e to the power 2, f, g to the power 3. And that is the correct answer. Let's see the penultimate example of number 6, and that is 15b to the power 3 divided by 3xy. Which of these laws is going to help us to see how to get the correct answer? It is this. Let's find out. Our a is 15, our b is this, b still, our c is 3, our d to power y is this x to power 1 and y to power 1 too. So in line with this law, this c divides the a, that is the constant here divides this constant. The same thing is going to happen. This 3 will divide this 15. If it happens, what we have is 5. Then next, this xy divides this b to the power 3, just like this d to the power y divided this b to the power x in this case. See it here. So the answer becomes 5b to the power 3 over xy. The last example highlights the importance of the fact that it is not all the time that division of unlike terms simplifies out. There was this caveat in the statement that came out of these 4 laws. That statement is that division of unlike terms simplifies out only if the constants possess common factor and or if there are similar or symbols which are alike. In this case, 5 and 2 are the constants. 5 and 2 do not have a whole number common factor. That means that we can't divide 5 by 2 to get anything simpler, which is which is a whole number. Because of that, we're not going to struggle to divide 5 by 2. Next, h to the power 3 and x to the power 2 are in no way similar. What it means is that this symbol and this symbol are not alike. So, what it means is that 5h to the power 3 and 2x to the power 2 are completely different. No common factor among the constants and no similarity among the symbols. Because of that, that condition attached to division of unlike terms will hold. When this happens, the answer is just as good as the operation. We then conclude that 5h to the power 3 divided by 2x to the power 2 is irreducible. Now the time has come for you to check whether you've been following what I've been saying since I began to talk about this section. Please watch out for an exercise. And here comes the checkpoint. It says, given that AB to the power x times CB to the power y is equal to AC bracket B raised to the power x plus y, AB to the power x divided by CB to the power y is equal to A over C bracket B raised to the power x minus y, and AB to the power x times CD to the power y is equal to AC bracket B to the power x d to the power y, and that A b to the power x divided by C d to the power y is equal to A over C bracket b to the power x over d to the power y. Simplify the following algebraic expressions. It simply means that there are 4 laws here regarding how to multiply and divide unlike terms. After seeing them, you are expected to simplify the following algebraic operations. That's number 1 is 7x to the power 3 times 2x times x. Check which of these laws that are going to apply to simplify this algebraic operation, and apply same and get the correct answer. The same goes to the remaining ones. They are ax to the power 2 times bx to the power 3 times cx. This number 2 tells us that it is not compulsory that at all times constants are the coefficients of the variables that play in multiplication of unlike terms. Here, a is supposed to be a constant, but it is a variable. It is an alphabet. B is also a constant, but an alphabet. C is also supposedly a constant, but an alphabet. Unlike others where we have to use pure constants in their place. Number 3, that is 6m to the power 5 divided by this 9m. Pick the law that is appropriate for simplifying this algebraic operation. Same goes to this number 4, 8x to the power 2 times 5y to the power 3 times z. And number 5, we have cg to the power 2 times dm to the power 3 times fz. Then number 6, 15y to the power 2 times c. Number 7, 21h to the power 5 divided by 7x to the power 6. Number 8, that's the last one, that is x to the power 2 times y to the power 3 times z. Of course, z is to the power 1.